Hello everyone, you are on Vectali, and this is the last four set of problems from work power energy of this advanced series. These kind of problems will develop your intuition towards the problem solving. Maybe two or three of the questions would be of much more difficulty than JEE Advanced, but you can develop intuition from those questions and apply in your later questions. First question. A block with mass m lies on an horizontal slippery surface and also touches a vertical wall. In the upper surface of the block, there is a cavity with the shape of half cylinder with radius r. A small pellet with mass m is released at the upper edge of the cavity on side closer to the wall. What is the maximum velocity of the block during its subsequent motion? Friction can be neglected. So what I was saying is this is a small pellet which we are keeping at this position and they are releasing it. Okay, they are asking us to find the maximum velocity of this block. To obtain a velocity v, that we have to find. Now, what happens is when this pellet reaches this position, it will attain maximum velocity. Because if I keep this as my reference position, if this is my reference, the potential energy over here is completely converted into the kinetic energy of the system. Okay, so at this position, the kinetic energy would be maximum. And you may think at this position too, but in this position, there is a minimum amount of potential energy and some amount of kinetic energy, and that kinetic energy is shared between these two. So anyway, the more velocity will be attained at this position, and till the block reaches over here, you won't observe the movement of this block because this will exert a force over in this direction. As a return reaction force, this would supply a force in this direction. Similarly, this reaction would be given here, and the wall will give the reaction force. Now, let's calculate the velocity v of the block. First, when the pellet is at the lowermost point, let's take, there will be a relative velocity between this pellet and the block m. So, I am considering this velocity with respect to ground as v2 and this velocity with respect to ground as v1. Okay. Now, we should find v1. The first thing, let's apply the conservation of momentum because initially there is no of the system because initially and finally there is no horizontal force, so momentum should be conserved in x direction of the whole system. So mv2 plus mv1 is supposed to be 0. This 0 is the initial momentum, and what next is we have to conserve energy. For conserving energy, what would we consider is, I am considering this as reference, so mgr is my initial potential energy, correct? So mgr is my initial potential energy. In final case, I have kinetic energies of both the bodies, half m v2 square plus half m v1 square. Now, with the momentum equation, what I get is I have to write v2 in terms of v1. So v2 is nothing but minus of capital M v1 by m. Okay, this I have to substitute it here. So what I get is mgr is equal to half m m square v1 square by m square plus half capital M into v1 square. Now what happens is mgr is equal to v1 square by 2 into m square by m plus capital M. So this thing can be written as 2 mgr whole divided by m square plus mm, and again the denominator m goes up. So what I get is v1 square. So upon taking square root, what I get is v1 is nothing but m into under root 2m, sorry, 2gr m into m plus m. This is the velocity of the block when it is at the maximum velocity, when this is the pellet is at the lowermost point. Okay, this approach is necessary. This is a very basic question, as this is the first question I am considering this as a basic question, and the next three questions would be very good questions. Question number 2. This is two identical beads A and B, each of mass m, connected by a light rod of length r root 2, can slide without friction on a fixed ring of radius r. The beads are also connected to fixed points C and D with identical elastic cords, each of force constant k and relaxed length r root 2, as shown in the figure. Initially, the cords coincide with diameters of the ring and the system is in equilibrium. Now, bead rod assembly is displaced slightly aside and released. Find the acceleration of point of intersection P of the cords immediately before a cord becomes relaxed. First, this is a very difficult question from Pathfinder Physics. Please listen this question solution carefully. First, this AB is a rod. AB is connected by a rod. A and B are beads. Now AC and BD are cords, okay, with the relaxed length R root 2. But now it is in diameter. So it's 2R. Initially, there is a force acting over here and here. It's pulling both A and B. If you displace it slightly, it would occur a simple harmonic motion. But what are we doing is, it is clear over here. Now the bead rod assembly is displaced slightly aside and released. Find the acceleration of point of intersection P of the cords immediately before a cord becomes relaxed. When will a cord become relaxed? A should go a distance of r root 2 from C. That is only possible when A reaches the point D, because these two are congruent triangles. ABP and DPC are congruent triangles. So this distance is r root 2. Then DC is also r root 2, because these two are r and the angle is also the same, 90 degrees. Because this is r root 2, r. This would be, of course, this is 90 degrees. Okay. So A should reach point D or B should reach point C. So let's consider the case where B reaches point C. When B reaches point C, where the string connecting B and D would lie along this direction. So this is the string connecting B and D. And the string connecting A and C would be along the rod AB itself. So this would be the string connecting A and C. So the point P, that is intersection of these two chords, will also locate here. Okay, this is the final question. They are asking the acceleration of the point of intersection of P of the chords immediately before the chords become relaxed. Now, but at this position, it will only have its velocity, right? P will, because now the strings have no extension. So it will cause no force. Okay, so there will be no acceleration due to these chords, because these are in relaxed state. Both the chords are in relaxed state. So we have to find any other acceleration is acting or what, like centripetal acceleration, those kind of things. So let's first find the locus of point P. Okay. Now, if you consider at any of the position in traveling from A goes from this position to this position, right? In any of the time, let's draw a situation. Now, this thing is r, correct? Because the radius, I'm just connecting all the 4 points with the center to mark it as radius, and this is r root 2 and this is also r root 2. So we can consider this as 90 degrees and this as 90 degrees always, because this is r, this is r, and this is r root 2. So this is of course 90 degrees in throughout the motion. It's like two perpendicular triangles, two right angle triangles, sorry, with the right angle vertex as the center is rotating with respect to each other. One is fixed and the other is rotating. That is a simple case we can see over here. Okay. Now what happens is, if this is 90 degree, this angle would be 45 degree. And if this is 90 degree, of course, what would I say is, this angle would be 45 degree. Why? Because if you take a circle, okay, now this is let this be the center. if this is 2 theta and this is also theta, sorry, this is not also, this is theta. This is a basic property from circles. So if I use this, if this is 90, this would be 45 degrees. So if this is 45 and this is 45, this is of course 90-degree, correct? Because in triangle ADP, it's supposed to follow the sum rule. That is, sum of angles is 180. So will be 90-degree. Similarly, this angle will also be 90-degree because AC is a single chord. So it can't go, this angle cannot be something less than or greater than 180 degrees. Okay. So this is also 90 degrees. So the angle PDC is nothing but 90 degrees. Now what can you consider? This is always. Now if DC is, let's assume a semicircle. Okay. Let this be the semicircle. Let me draw a circle there. If this is a circle, sorry. If this is a circle, its center, if I take diameter, the diameter always subtends 90-degree at the vertex, correct? So this is also another property from the circles. So if this is 90-degree and let's consider DC as diameter. So the locus of P would be the quarter circle with center as midpoint of D and C, correct? So locus of P will be a quadrant of circle with center as midpoint of D and C. Okay. Now you can see this throughout the question. So we can say, sorry, I'm not good at drawing, but let me try to sketch the circle. Now, actually, this should pass through the center too. So let's consider this is a semicircle. Okay. Now P is over here. The locus of P should be along this line. So will be the locus of P. P travels through this path from center to this point. Now, if you see, yeah, this works. Now, P is right now here. Now, the only acceleration P can have is centripetal acceleration about this point. Let's be C dash. So the only acceleration C can have, only acceleration sorry, point P can have is centripetal one. So we are going to calculate it. Okay. Now first, let's calculate the velocity of P at this point, at this particular state. Okay. The velocity of P is nothing but the velocity of B at this point. So let's calculate the velocity of B by using the conservation of energy. By conservation of energy, initially the whole system has, this is, let's assume this is in a horizontal plane, because if we include gravity, this thing would become, sorry, the gravity is there. One sec. Sorry, the gravity is, we are not going to consider the gravity here because let's consider it to be a horizontal plane. If we involve gravity, the system will get much more complicated, and they did not mention about the gravity too. So let's consider the initial potential energy as the potential energy stored in the chords AC and BD. So that potential energy, so energy is nothing but initial and final are same, so I'm just terming it as energy half k into 2r minus r root 2 whole square into 2 because I have two strings. And in the final case, they both have zero extension, so they have zero potential energy in them. But the beads A and B have some velocity, that is tangential velocity. It's tangential along this direction, correct? So it's tangential here. If you want to term this direction, it's like this is V. Okay, this is twice of half mv square. So let's cancel this term. So what I get is v square is nothing but, okay, right? Let me write mv square is nothing but k into 2r minus r root 2 the whole square. Now, if you see clearly, we want this velocity in this direction. Let's v dash. So v dash is nothing but the component of v with this angle. This angle is 45 degrees. Okay, because this is a tangent over here, and this would be another 45, and this is 90. This is of course 90. So this should supposed to be tangent for this circle, the big circle. So this is 45 and this is 45. So this is also 45 degrees. So what I get is we have to find v cos 45, that is v by root 2. So we want m v dash square by r root 2 by 2, because r root 2 by 2, which is r by root 2, is the distance from point C dash to point P. This is what we want. This is the centripetal force. The acceleration is given by v dash square by r by 2 root 2. So v dash square is nothing but v square by 2. v square by v square divided by r root 2. This is the final answer we want. And what is v square? K into 2r minus r root 2 the whole square by mr into root 2. This is the final answer. This is a very lengthy question because we have to understand the concept. We have to apply the two concepts of circles and all. This takes time. If you have any of the doubt in this question, just comment it down. I will explain it. Question number 3. This is an interesting question from Irido. A horizontal plane supports a stationary vertical cylinder of radius r and a disk A attached to the cylinder by a horizontal thread AB of length L0. An initial velocity v0 is imparted to the disk as shown in the figure. How long will it move along the plane until it strikes against the cylinder? The friction is assumed to be absent. Now, if you see here, this is a cylinder we are seeing from the top view. This is a cylinder and A is a disk. We are attaching this end of the thread AB over here. Now we are giving it a perpendicular velocity v0. Okay, so it will curl and for it's in somewhere a position like here or here maybe. Okay, now the points we have to think about is the magnitude of v0 will not change because always the force acting in this situation is tensile force is always perpendicular to v0. So it will only change the direction, not the magnitude. So throughout the journey the velocity will be v0. Okay, now will this L not be the same? Let's take a position where when this particular disk reaches here, if you see the center would be around here, correct? And because the remaining length will be curled across here and the center will be over here. So that is why that is what I have drawn over here. So the remaining length would be L minus R theta, correct? This is capital R. So the remaining length is L naught minus R theta, and this is L naught. Okay. Now, since this is perpendicular, this will also be perpendicular. This is perpendicular because these are tangents. Always the string would be tangential to the radius. Correct. So this is 90 and this is also 90. This is 90. Now this forms a quadrilateral, right? So these two are 90 and this is theta. So this is supposed to be 180 minus theta. And what about this? This would be theta. So for every theta change over here, sorry, if for every d theta change over here, you will also get d theta change over here. So for every d theta here, you will get d theta change over here. So the length transferred in d theta is nothing but arc length, that is ds is nothing but L naught minus r theta into d theta. Okay. Now we need the total arc length because they are asking the time, actually how long. They are asking the time. We have the velocity. We have to find the complete arc length. So arc length I am going to integrate it. So what I get is integral ds is nothing but integral of L naught minus r theta into d theta. Okay. Now the range of theta is initially the theta angle theta is 0. What about the final? Final, if you see the image, you will think it as 2 pi. But we don't know, we don't have the perfect relation between L naught and for this to be 2 pi, L naught is supposed to be 2 pi r. Correct. But we don't know the relation. So the final point of the instantaneous center would be L naught by r. Okay. This would be the final angle. Let's check it here. If it is 2 pi, we will get L naught by r as 2 pi. Right? If it is pi by 2, we will get L naught by r as pi by 2. Okay. So we don't know the exact value. So we are writing L naught by r. And this question involves the concept of instantaneous center. Okay. Because initially the center is here, 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 and it goes till it reaches the length L naught. Now the arc length is nothing but L naught into theta minus r theta square by 2 from 0 to L naught by r. So S is nothing but L naught square by r minus r by 2 L naught square by r square. So what you get is L naught square divided by 2r. So this is a total arc length. So total time taken is nothing but distance covered by velocity v naught. So L naught square by 2r v naught. Everything is simple. The first important thing you have to do is find the relation between this theta and this theta. That is what the necessary part of this question. You have to use geometry over here. That's how the work power energy questions are completed. We have uploaded the PDF in the post section. Kindly do practice it. If you have any doubts, just comment down. We are here to support you. Thank you. Stay tuned.